Hello and welcome to the lecture 3 of this online lecture series on complex number. In this lecture, we are going to learn de Moivre's theorem. De Moivre's theorem, let's see its statement. When n is an integer, positive or negative, and theta is real number, then cos theta plus I sin theta whole to the power n is equal to cos n theta plus I sin n theta. So this is the statement of the de Moivre's theorem when n is an integer, positive, negative. But when n is a fraction, the positive or negative fraction, and theta is real number, then cos n theta plus I sin n theta is one of the value of the cos theta plus I sin theta whole to the power n. We are going to prove this theorem in three cases. Case 1, when n is a positive integer. Case 2, when n is a negative integer. And case 3, when n is a fraction, positive or negative. So let's see the case 1. Case 1, when n is a positive integer, here we are going to use principle of mathematical induction to prove this case. The theorem is true for n is equal to 1. So if I put in place of n is equal to 1, we'll get cos theta plus I sin theta. That can be written as cos 1 theta plus I sin 1 theta. So the theorem is true for n is equal to 1. Now let us assume that the theorem is true for n is equal to m. This is our assumption. So m is a positive integer. Cos theta plus I sin theta whole to the power m is equal to cos m theta plus I sin m theta. This is our assumption. Now we have to prove that the theorem is also true for m plus 1. Then by the principle of mathematical induction, the theorem is true for all positive integer n. Therefore, cos theta plus I sin theta whole to the power m plus 1 can be written as cos theta plus I sin theta whole to the power m into cos theta plus I sin theta. In the next step, see, cos theta plus I sin theta whole to the power m is equal to cos m theta plus I sin m theta by our assumption, this assumption. Now if I multiply this two product, we will get cos m theta minus sin m theta sin theta plus I into cos m theta sin theta plus sin m theta cos theta. This is the this thing comes from the multiplication of these two product. Here this means cos m theta plus theta, that can be written as cos of m plus 1 theta. Similarly, this quantity can be written as sin m theta plus theta, which is equal to sin m plus 1 theta. So this one is theta. So I'm getting this quantity is equal to cos m plus 1 theta here, and this quantity is equal to sin m plus 1 theta, so here. Now from here we can say that this shows that the theorem is true for n is equal to m plus 1. So instead of n, I am writing over here m plus 1. I am getting this term. That means the theorem is true for n is equal to m plus 1. Therefore, by principle of mathematical induction, the theorem is true for all positive integer n. Now case 2, when n is negative integer. When n is negative integer, so n is negative, so I can write n is equal to minus m, where this m is positive integer. Now cos theta plus I sin theta whole to the power n is equal to cos theta plus I sin theta whole to the power minus m, because n is equal to minus m. So this power is minus m, so it will be come over here in the denominator. Now it has become positive, m is positive, so I can apply the case 1. That means it will be cos theta plus I sin theta whole to the power m will be cos m theta plus I sin m theta by case 1. That is the case when the power is positive integer. Now multiplying and dividing by cos m theta plus I sin m theta, we will get we will get cos m theta plus minus I sin m theta. Because this denominator is 1, it will be cos square m theta plus sin square m theta, that is 1. Now cos theta plus I sin theta all to the power n is equal to cos of m is minus n, m is equal to minus n theta plus I sin minus n theta. So instead of m I am writing minus n. That means cos theta plus I sin theta whole to the power n is equal to cos n theta plus I sin n theta. Because cos of minus n minus theta is equal to cos theta and sine of minus theta is equal to minus sin theta. That sine in this, that minus and this minus will make it positive. Hence the theorem is true for negative integer n also. Case 3, when n is a fraction, positive or negative fraction. Since n is a fraction, I can write n is equal to p by q form, where p and q are integer and this denominator q is greater than 1 and the p may be positive or negative. Cos n theta plus I sin n theta whole to the power q can be written as cos p by q theta plus I sin p by q theta, because n is equal to p by q, n is equal to p by q, and this can be written as cos p theta plus I sin p theta, because when you take this q inside here, this q will get cancelled. We are left with p theta and here also p theta. So which is equal to cos theta plus I sin theta whole to the power p. Taking this p outside, taking this p, will get over here in the power by case 1 and case 2. So that means cos p by q theta plus I sin p by q theta whole to the power q is equal to cos theta plus I sin theta whole to the power p. That means this quantity is equal to this quantity. So this power will come over here in the denominator. So cos p by q theta plus I sin p by q theta is equal to cos theta plus I sin theta whole to the power p by q, and this means this is the one of the value of this quantity. That is cos p by q theta plus I sin p by q theta is one of the value of the cos theta plus I sin theta whole to the power p by q, and we know that this p by q is n. So I can write cos n theta plus I sin n theta is one of the value of cos theta plus I sin theta whole to the power n when n is a fraction, positive or negative. Because we know that the qth root of something will have q value and one of the value is this. Out of that q value, one of the value is this. So this is one of the value. Corollary, when instead of plus now we have minus over here, cos theta minus I sin theta whole to the power n, and it will be cos n theta minus I sin n theta when n is a integer positive or negative, and cos n theta minus I sin n theta is one of the value of cos theta minus I sin theta whole to the power n when n is a fraction. Now next theorem is let z be a complex number and n be a positive integer, then z to the power n have n distinct value. So this is the theorem. Now we are going to prove this theorem. Suppose let z is equal to r cos theta plus I sin theta. That means polar representation of z is equal to r cos theta plus I sin theta, where this theta is the principal argument and r is greater than 0. Let z to the power 1 by n is equal to w. Nth root of z is equal to w, which is a complex number. Let it be rho cos phi plus I sin phi. Then from here I will get w to the power n is equal to z, and w to the power n means this quantity to the power n, that means rho to the power n cos n phi plus I sin n phi. Because if you take this n over here in the power by the De Moivre's theorem, this n will come over here in So which is equal to r cos theta plus I sin theta, because we know that z is equal to r cos theta plus I sin theta. Now comparing these two, we'll get rho to the power n cos n phi is equal to r cos theta, and rho to the power n sin phi is equal to sin theta. Comparing real part and imaginary part. Now rho to the power n is equal to r, rho is equal to nth root of r, where nth root of r is a positive nth root of r, because r is always greater than 0. Here it is mentioned over here, r is greater than 0. And n phi, this n phi is equal to theta plus 2k pi, because n phi may not be principal argument but theta is principal argument. So if theta is principal argument, we cannot assure that the n phi is also principal. So instead of theta, we'll write additional quantity 2k pi, where k is an integer. So from here, phi is equal to 2k pi plus theta by n, and now putting the value of phi and r here, we'll get w is equal to rho is equal to nth root of r, cos of phi means 2k pi plus theta by n, and I sin 2k pi plus theta by n. So k is an integer. For different value of k, there are infinitely many value of w, that is z to the power n. W means z to the power n over here. So we'll get infinitely many value of z to the power n for different value of k. But this is not so. The value of zm, zn is not infinite, it is actually finite. Let zm be the denote the value of w corresponding to k is equal to m. Then zm is equal to nth root of r 2m pi plus theta by n, 2m pi plus theta by n here also. So here we have put k is equal to m. We prove that z0, z1, z2, zn are all distinct value of w, and every other value of w for k other than this number takes one of the value of this distinct value. That means if I take z to the power zn by zn plus 1, this value will be equal to one of the value from this quantity. To prove these are distinct, this quantity are distinct, let us assume that two number are equal. Zp is equal to zq, where this p and q are integer less than n minus 1, less than equal to n minus 1, and p is greater than q. Now if they are equal, so their argument are also equal. So that means they are 2 pi plus 5 theta by n is equal to 2q pi plus theta by n plus 2rs. Because the argument is principal, it's not principal, so we have to put this additional quantity to 2s pi over here, where s is an integer. Now 2p pi plus theta by n, I am taking this on the other side, so it will be minus 2p pi plus phi by n is equal to rs, and after simplification we are getting 2 pi p minus q by n is equal to 2 sr. So these two quantity are equal. That means pq by n is equal to s. So pq by n is equal to s means pq by n is an integer. We know that this p and q are less than n minus 1, so this is only possible when p is equal to q. As we know that this p and q are integer which is less than equal to n minus 1. So if they are less than n minus 1 and their difference will be less than n minus 1, so the lesser quantity divided by this greater quantity is not an integer. This is only possible when p and q are equal, because p minus q is less than n. So that means these are distinct value. So whenever we we consider Zp is equal to Zq, we are getting P is equal to Q. So this value Z0, Z1, Z2, Zn minus 1 are all distinct value. Now we prove that any value of W for k runs through the integer 0 to n minus 1 is one of the value of this Z0 to Zn minus 1. Let us consider Zt, then t is other than this quantity, that means 0 to n minus 1. So I'm taking t as greater than n minus 1. So by the division algorithm there exists lambda and mu. So t can be written as n lambda plus mu, where this mu is less than n, 0 less than equal to mu less than n. This is by division algorithm. So zt will be equal to nth root of r cos 2t pi plus theta by n plus I sin 2t pi by 2t pi plus theta by n. I'm putting t is equal to t instead of k. T is how much? T is m lambda plus mu. So if I put here instead of t n lambda plus mu, we are getting this quantity. So which is equal to 2 cos mu pi plus theta by n plus I sin mu pi plus theta by n. Because this is a multiple of 2 pi, that means 360. It will give you the cos of 360 multiple of 360 plus this angle is equal to cos of this angle, and similar for the sine of this angle, which is this means this is equal to z mu. So that means we have taken zt, t is other than this number, but we are getting this equal to z mu, and mu is less than n, that means mu is one of this number. So this means since 0 is less than mu is less than equal to n, it follows that there are n distinct value of z to the power n. So, and they are nth root of r cos 2k pi plus theta by n plus I sin 2k pi plus theta by n, where k is equal to 0, 1, 2 up to n minus 1. Note, nth root of r cos 2k pi plus theta by n plus I sin 2k pi plus theta by n has same modulus, and their argument are so when you put a k is equal to 0, you will get n by theta by n, and when you put k is equal to 1, you will get 2 pi by n plus theta by n, and when you put k is equal to 2, you will get this argument, and so on. Corresponding to k is equal to 0 is called the principal nth root of z. So when you put k is equal to 0, we are getting the nth root of z. This nth root of z is called the principal nth root of z.